Testing, can you hear me? Testing, can you hear me? Testing one last time. All right. My video is public now, so I'm going to be reading about computer architecture again. Hold on. And I have the book in the description below, so you can read it if you want. I'm going to be reading the same book. So last time I was learning about x86, but I took a long gap because I was studying probability and statistics in between. So I would revise some of the subchapters first. It's quite a long chapter, this x86 one. And I also found an x86 online compiler. I tried to use that as well. Okay, so I'm going to revise this from the. I'm going to rush through what I've already read before. So, brief history. Let's start out by noting that x86 is not one language. It is actually a family of assembly languages with a very interesting history. Intel released the 8086 microprocessor in 1978 and called it 8086. Why did they call it 8086 though? It was Intel's first 16-bit microprocessor. The microprocessor proved to be very successful in the market and succeeded in displacing other 8-bit competitors at that time. This motivated Intel to continue this line of processors. Intel then designed the 8186 and 8286 processors in 1982. 8186 was aimed at embedded processor market and 8286 was aimed at desktops. Both of them were fairly successful and helped establish Intel processors firmly in the desktop market. Those days, IBM was the biggest vendor of PCs, and most IBM PCs used Intel processors. The rapid proliferation of PCs led Intel to release two more processors, 8386 and 8486, in 1985 and 1989, respectively. These were 32-bit processors. Note that as Intel moved from 8086 to 8486, it continuously added more and more instructions to the instruction set. However, it also maintained backward compatibility. This means that any program meant to run on an 8086 machine could also run on an 8486 machine, uh, could also run on an 8486 machine. Second, it also maintained a consistent assembly language format for this family of processors whose name ended with 86. Over time, this family of processors came to be known as x86. Gradually, other companies started using the x86 instruction set. Most notably, AMD started designing and selling x86 based processors. AMD released the KB, K6, and K7 processors in the mid 90s based on the 32 bit x86 instruction set. It also introduced the x86 64 instruction set in 2003, which was 64 bit extension to the standard 32 bit x86 Intel ISA. Many other vendors, such as VIA and Transmeta, also started manufacturing x86 based processors starting from 2000. Each vendor has historically taken the liberty to add new instructions to the base x86 instruction set. For example, Intel has proposed many extensions over the year, such as Intel MMX, SSE 1, 2, 3, and 4. The number of x86 instructions are more than 900 as of the number of x86 instructions are more than 900 as of 2012. Similarly, AMD introduced 3D Now instruction set, and NVIDIA introduced its custom extension. The rich history of x86 processors has led to numerous extensions of the basic instruction set. There are numerous assemblers that have their unique syntax. Almost all x86 vendors today support hundreds of instructions. Current 64 Intel processors support 16-bit and 32-bit code that dates way back to the original 8086. If we try to classify the entire family tree of x86 ISAs, we can probably divide them as 16, 32, and 64-bit instruction sets. 16 bits are rarely used, 32 bits are extremely popular in smartphones, embedded in laptop netbook markets. The 64-bit, also known as x86 64, are mainly meant for workstation class, desktops, laptops, and servers. Other than minor syntactic differences, the assembly languages for these instruction sets are mostly the same. Hence, learning one is sufficient. We focus on 32-bit because in our opinion, it falls in the middle of the usage spectrum of the x86 ISA, which I mentioned the minor syntactical differences with other flavors of x86 whenever the need arises. The main feature, it is a complex instruction set computer, ISA. The C stands for or does it stand for compiler? I can't remember. ISA instructions have varying lengths, and operands that also do not have fixed length. There are at least 300 scalar instructions. This number keeps increasing every year. Almost all the instructions have a memory operand. In fact, most instructions allow a source and a destination memory operand. Most are in two address format. For example, the assembly to add two registers, EAX and EBX, is add EAX, EBX. Okay. Has many complicated addressing modes. It does not have a return address register. Function call and return instructions save and retrieve the return address from the stack. Like ARM and Simple RISC, x86 has a flag register that saves the outcome of the last comparison. The flags register is used by conditional branch instructions. Unlike Simple RISC, x86 instructions do not see a unified view of the instruction and data memory. x86 memory is segmented. This means that instructions and data reside in different memory regions, known as segments. Instructions and data reside in segments. Okay. It is true that x86 architecture is a complex instruction set. There's hundreds of opcodes and many addressing modes. Nevertheless, we are sure that at the end of the chapter, the reader will concur with us that the x86 instruction set is in reality a fairly simple instruction set, easy to understand, and is very elegant. So the x86 machine model, we have the 64-bit, 32-bit, and the 16-bit. Okay. The 16 and 32-bit x86 ISAs have 8 general purpose registers. Okay, the 16 one and the 32-bit one, they have 8 general purpose, namely A, B, C, D, E, F, and G. A, B, C, D. Where's E, F, and G? A, B, C, D, E, F, and G. Hold on, let me see that again. They decided to keep the 4 registers A, B, C, D and suffix them with the X tag, X for extended. Thus, the 4 general purpose registers got renamed AX, BX, CX, and DX. Additionally, the designers of the 8086 machine decided to retain some 16-bit registers, namely the stack pointer, SP, and the register to save the PC IP. Stack pointer, and then where do you save the PC? The designers also introduced 3 extra registers in their design: base pointer, starting index, and destination index. Base pointer, starting, destination. Oh, IP is over here. It's stored separately. The intention of adding the BP register was to save the value of the stack pointer at the beginning of the function. Compilers are expected to set SP equal to BP at the end of the function. This operation destroys the stack frame of the callee function. The registers SI and DI are used by the rep instruction that repeats a certain operation. Rep instruction. Rep instruction. I don't see any rep here. What does rep do again? Single rep instruction is equivalent to a for loop. Rep is an instruction. Oh, it's not a register. 8086 processor had 8 16-bit general purpose registers. It was further possible to access 2 bytes in the registers AX to DX. For example, the lower byte in the x86 register can be addressed as AL and the upper byte can be addressed as AH. 16-bit x86 instructions can use a combination of 8-bit and 16-bit operands. The 8086 processor had 2 special purpose registers. The first IP contained the PC. The PC is typically not accessible to programmers on x86 machine. The second special purpose register is the flags register that saves the result of the last comparison. The flags register is used by subsequent conditional branch instructions to compute the outcome of the branch. Aren't there multiple flags? Oh, we are saving 16 bits for the flags, right? So it's like you can save 16 flags in total, right? In the mid-80s, when Intel decided to extend the 8086 design to support 32-bit registers, it decided to keep the same set of registers: a general purpose, IP, and flags. However, it extended their name by adding an E prefix. Okay, so for 32 bits, we have E over here. 32 bits, we have E over here. And these 4 general purpose ones have the higher 8-bit and lower 8-bit. Okay, now what are these are the different flags, right? 16-bit segment registers. EAX is the 32-bit version of EX. To maintain backward compatibility with the 8086, the lower 16 bits of EX can be addressed as AX. The 2 bytes in AX can be addressed as AH and AL. Okay. In a 32-bit machine, the stack pointer is stored in ESP and the PC is stored in EIP and the flags are stored in E-flags register. There are many advantages to this strategy. The first is that 8086 code can run on a 32-bit x86 processor seamlessly. All of its registers are defined in a 32-bit ISA. This is because each 16-bit register is presented by the lower 16 bits of a 32-bit register. Hence, there are no issues with backward compatibility. Second, we do not need to add new registers because we simply extend each 16-bit register with 16 additional bits. We refer to the new register with the new name 16-bit name prefixed with E. Exactly the same pattern was followed while extending the x86 ISA to create the 64-bit and x86-64 ISA. The first letter was replaced from E to R to convert a 32-bit register to a 64-bit register. For example, the register RAX is the 64-bit version of EAX. Its lower 32 bits can be addressed as EAX. The connotation of AX, AH, and AL remains the same as before. Additionally, x86-64 introduced 8 general purpose registers, namely R8 to R15. So before we had this, but the 64-bit also introduced R8 to R15. The registers RAX as a 64-bit version of EX. Slower 32 bits can be addressed as EX. Connotation of AX, AH, and AN remains the same as before. 64-bit PC is saved in the RIP register and the flags are stored in the R flags register. RIP. Let us now quickly discuss the structure of the E flags register. Like ARM and x86, the flag register contains a set of fields where each field or bit indicates the status of the execution of the instruction that has set it. It is called E flags in 32-bit. Okay, let's see. So sign flag, zero flag, carry flag, overflow. The floating point instructions in x86 have a dual view of floating point register file. They can see them either as normal registers or a set of registers organized as a stack. Let us elaborate. To start out, x86 defines 8 floating point registers named ST0, S to ST7. Where is this? What is this ST0 to ST7? x86 defines 8 floating point registers. We're talking about 32 bits, right? These are 80 bit. Oh, okay. So these are separate registers that are 80 bit. The x86 floating point format has a 64 bit mantissa and a 15 bit exponent. It is thus more precise than double precision numbers. The registers ST0 to ST7 are organized as a stack. So ST0 is the top, ST7 is the bottom. Figure 5.2. Okay. Additionally, x86 has a tag register that maintains the status of each register in the stack. The tag register has 8 fields, one field for one register. Each field contains 2 bits. If the value of these bits is 00, then the corresponding register contains valid data. If the value is 1, then the register contains a 0. If it is 1, then the register is empty. 10 is reserved for special purposes. We should refer to the stack of registers as a floating point stack or simply the FP stack. The tag register has 8 fields, one field for one register. Tag register that maintains the status of each register in the stack. Okay, I need to see okay. The registers ST0 to ST7 are positioned on the FP stack. ST0 is always on the top, ST7 is the bottom. We push a data onto the FP stack, then the contents of each register get transferred to the register below it. If the stack is full, then the stack overflow occurs. This situation needs to be avoided. Most floating point instructions operate on data values saved on at the top of the stack. They pop the source operand and they push the destination operand. Let us now describe the functionality of the segment registers. In the view of the memory, x86 instructions can have two views of memory. The first view is like ARM and Simple RISC, which views memory as one large array of bytes that stores code and data. Okay, so what's the second view? This is known as a linear memory model. In comparison, the segmented memory model views memory as consisting of fixed size segments, where each segment is tailored to store one type of data, such as code, stack data, or heap data. We shall not discuss the linear model of memory because we have seen it before in chapter 3. So linear views the entire memory as one large array of bytes that saves both code and data. Segmented views memory as a sequence of multiple fixed size segments. Code, data, and the stack have their own segments. Let us define the term address space as the set of all memory addresses accessible to a program. The aim of the segmented memory model is to divide the address space into separate smaller address spaces. Each address spaces can be specialized to store a specific type of information such as code or data. There are two reasons for using segmentation. The first is historical. In the early days, different parts of the program were physically saved at different locations. The code was saved on punch cards and the memory data was stored in DRAM memories. Hence, it was necessary to partition the address space among the devices that stored all the information that a program required. The reason is not valid anymore. Nowadays, all the information a program requires is typically stored at the same place. However, we still need segmentation to enforce security. Hackers and viruses typically try to change the code of a program and insert their own code. Thus, a normal program can exhibit malicious behavior and can corrupt data or transfer sensitive data to third parties. To ensure added protection, the code region is saved in the code segment. Most systems do not allow normal instructions to modify the code segment. Segmentation in x86. The x86 designers had 6 segment registers that stored the most significant 16 bit of the starting location of the segment. The remaining bits were assumed to be all zeros. The CS register stored the up 16 bits of the starting location of the code segment. Similarly, the DS register stored the upper 16 bits of the starting location of the data segment. The SS register stored the corresponding set of bits for the stack segment. CS, DS, and SS. Oh, that was the separate part, right? CS, DS, and SS. Code, data, stack. Where did it go? Where was I? Here. Code, data, stack. The ES extra segment, FS, and GS registers could be used to store information for additional user-defined segments. Till date, all x86 processors have preserved this model. Contents of the instructions are saved in the code segment, and the data that a program accesses is saved in the data segment. In most small programs, the stack and data segments are the same. In 8086 processors, the memory address was 20 bits wide. Hence, to obtain the final address node, also known as the linear address, the 8086 processor first shifted the contents of the segment register 4 positions to the left to obtain the starting location of the segment. It then added this address with the memory address specified by the instruction. We can think of memory address specified by an instruction as an offset in the segment, where the starting memory location of the segment is indicated by the appropriate segment register. This strategy served the needs of the 8086 designers well. However, this strategy is not suitable for 32 and 64-bit machines. In this case, the memory addresses are 32-bit and 64 bits wide respectively. Thus, the segment registers need to be wider. In the interest of backward compatibility, designers did not touch the segment registers. They just changed the semantics of its content for newer processors. Instead of saving the upper 16 bits of the starting location of a segment, the registers now contain a segment ID. Segment ID uniquely identifies a segment across all the programs running in the system. To get the starting location, 32 and 64-bit processors uh, look up a segment descriptor table with 13 bits, 4 to 16 of the segment ID. 13 bits can specify 8,192 entries, which is more than significant for all programs in the system. Hold on a minute. Modern modern x86 processors have two kinds of segment descriptor tables, namely the local descriptor table and a global descriptor table. The local is typically local to a process, contains the details of the segment for that process. The LTD is normally not used nowadays because programs do not use a lot of segments. Comparatively, there is only one system level GTT. The GTT can contain up to 8,191 entries. The first entry is reserved. Each entry in the GTT contains the starting address of the segment, the size of the segment, and the privileges required to access the segment. Every memory access needs to go through the GTT for fetching the starting address of a segment. Hold on a minute. I left an application open. I was just closing it. This unnecessarily lengthens the critical part of the memory request and creates contention at the GTT. To make the access of the GTT faster, modern processors have a small structure called segment descriptor cache that stores a few entries of the GTT that are relevant to the currently executing process. The cache typically stores the details of all the segments that the frequently running processors use. This strategy ensures that we do not need to access the GTT on every memory access. The small and fast descriptor cache is sufficient. After accessing the descriptor cache or the GTT, x86 processors get the starting address of the segment. Subsequently, generate the memory address by adding the address specified in the instruction while the starting address of the segment. This address is then passed on to the memory system. Process, it is the running instance of a program. LTD, it is per process. Save the description of all the segments that a process uses. GTT, it's confusing to say it. GDT, similar to LTT, but it's system level. Addressing modes for specifying immediates. Best thing about x86, there's no size restriction on immediates. Immediates can be as large as the size of the register. For example, a 32-bit system, the size of the immediate can be as large as 32 bits. Depending upon the assembly language, we can specify immediates in the hex format, binary format, or in decimal. Most of the time, programmers prefer hex or decimal. For hexadecimal numbers, most assemblers allow us to specify the numbers with the standard 0x prefix. Okay. For negative numbers, we simply put a dash before. Okay. Specifying registers. All registers in x86 are addressed by their names. For example, the general purpose registers on a 32-bit machine are addressed as EX, EBX, and EDI, according to the rules mentioned in section 5.2.1. Yeah, what were the rules again? According to the rules, okay, over here. We can use 16-bit register names in 32-bit mode. We can use 16 and 32-bit registers addressing in 64-bit mode. Not that we cannot do the reverse. Okay. x86 supports a variety of addressing modes for main memory. In specific, it supports the register indirect base offset base index and base index offset addressing mode as mentioned. So wait, if we want to specify a memory address, we can use the base index scale offset. Or we can specify a segment, and then the rest of the bit are stored in the register. So we can specify a memory location like that. Plus, okay, offset, I understand. What is this? Scale plus a scale. Okay. 1248. How much you want to scale? I think the value over here times this, and then an offset. Equation 5.1 shows the generic format of the memory address in a 32-bit version of x86. The interesting aspect of x86 memory addressing is that all of these fields are optional. Hence, it is possible to have numerous addressing modes. What do you mean all of the fields are optional? So we can have something like, for example, just 5. Let us first consider the addressing mode that require a base register. With the base register, we can optionally specify segment register. Okay, segment. If we do not specify a segment register, then the hardware assumes the default segment. D is for data, S is for stack, and C is for code. We can subsequently specify an index. The index contained in another register, including ESP. We can optionally multiply the index with the power of 2. Lastly, we can specify a 32-bit offset known as displacement. Now let us look at addressing modes that do not require a base register. We can use an index register and optionally scale it by 1, 2, 4, or 8. For example, we can specify we want to access the memory address equal to 2 times ECX. This approach uses the scaled index addressing mode. We can optionally add a fixed offset known as the displacement to the address. Lastly, it is possible to specify the entire 32-bit address in the displacement field and not specify any register at all. This approach is typically used in the operating system code to directly operate on memory addresses. Regular assembly programmers need to strictly avoid such direct memory addressing because most of the time we are not aware of the exact memory addresses. For example, the starting memory address of a stack pointer is typically allocated at runtime in modern systems and tend to vary across runs. Secondly, this is not portable and elegant approach. It is only meant for operating system writers. Let us explain with examples. See table 5.2. Okay, so EAX is register indirect. Okay. So if I just specify the memory address, that's memory direct. But if I want to indirectly specify, I can use a register. That would be register indirect. The value of this address is stored in EX. I can have EX plus some other register times 2. Then I have the base plus scale index. Base scale index. Okay. And then I have base scale index offset, base offset, scale index. This is just a subset, right? I can have. Can I also have maybe base offset, scale index offset, or just base offset, scale index? Can I have scale index offset? The fixed offset used by specifying the effective address of a memory operand is known as a displacement. There are various x86 assemblers such as Ma- MASM, NASM, and the GNU assembler. In this book, we shall present code snippets that have been tested with NASM assembler. Popular NASM assembler is freely available at NAS and is known to work on a variety of platforms, including Windows, Mac, and different flavors of Linux. Note that we should mostly avoid using NASM specific features and we should keep the presentation of assembly code very generic. Our assembly code should be compatible with any assembler that supports the Intel format for x86 assemblers. The one only major feature of NASM that we should use is that commands begin with semicolon character. So the structure looks like this: label, assembly instructions, and then a comment. I found this online compiler. If I execute it, it says JDoodle in action running the program. Okay, it takes quite long. Sum of x and y is 8. So x is stored in EAX, y is stored in EBX. Why they're subtracting 0? So over here they said x db5, y db3. Okay. Oh, I think 5 is like character. It's like text. So they're no wait. Oh yeah. 5 is alphanumeric and they're subtracting the alphanumeric 0 because 5, the ASCII of the letter of the character 5 is not is a larger number, right? So you're subtracting it with the character 0. So we get the number 5. I think that's what they're doing. Y is subtracting 0. And then we are adding these two. Oh, and then we are adding EX to 0 back. And then we are storing EX to the sum variable and some message db, the sum of xy is. Okay, so message is to, wait, what? Move message to ECX. They mean the address of this, right? And then move len to edx. Okay, I don't know what's happening here. Moving 1, moving 4. What is this BSS? Okay. Oops. I'll just close this. For an assembly instruction, the label and comment are optional. Alternatively, we can have a label or comment or a combination of both in a single line. Now code we can use labels starting with a dot. However, labels can start with regular alphabets and other special characters also. For a detailed description, readers can refer to the NASM documentation. You have the opcode and operand, comma, operand 2. Opcode, operand 2. In overwhelmingly majority of x86 instructions are in 0, 1, and 2 address formats. 0 instructions are like nope, no operation, and simplex do not require any operations. 1 address format instructions have a single source operand. In this case, the destination operand is equal to the source operand. Example instruction not. Okay. The move instruction, you have move, register or memory, and then register memory or immediate. You move the location, or like whatever is stored in EBX to EX. I mean, that's what's happening here. Write an x86 assembly instruction to set the value of ABX to -17. All right. And then we have contents of ESP minus EX times 4 minus 12. We have this. The square bracket means memory address, right? Memory address of X. Write an x86 assembly instruction that store the contents of EDX. So answer. Okay. Move SX and move ZX instruction. The simple move instruction assumes that the sizes of the operands are the same. However, sometimes we face the need for saving a smaller register or memory operand in a larger register. For example, if you save the 16-bit register AX in EBX, then we need to have two options. We can either extend the sign of the input operand or pad it with zeros. The move SX instruction copies a smaller register or memory operand to a larger register and extends its sign. For example, the following code snippets extend the sign of BX, saves the results in EAX. So wait, let me see what's happening. The second operand is either 8 or 16 bits. So from BX, we are going to EAX. Sign extended. Following code snippet extends the sign of BX and saves the result to EX. The move CX instruction is defined on the same line. However, instead of performing a sign extension, it pads the MBS bits with zeros. Most significant bits with zeros, right? So BX to EX. If we just say move, wouldn't the most significant bits also have zeros? Or do they have garbage values? The atomic exchange instruction. The exchange instruction swaps the contents of the first and second operands. Here also we cannot have two memory operands. The instruction ensures that before the operation is done, no other operation can read temporary values. For example, if we are swapping values of EX and the memory operand EBX, there might be an intermediate point in the execution where the contents of EX are updated but the contents of EBX are not updated. x86 processor does not allow other threads to read the contents of EBX at this point. It makes other conflicting instructions in other execution threads wait till the exchange instruction completes. This property is known as atomicity. Atomicity. I'm pronouncing it right. We learn this in operating systems, right? An instruction is atomic if it appears to execute instantaneously. Most of the time, atomic instructions such as exchange are used for implementing data structures that are shared among multiple threads. The reader should read chapter 12 for a detailed discussion on parallel software that uses multiple threads. An instruction is atomic if it appears to execute instantaneously. So atomic means there won't be any context switch when that instruction is happening, right? Write a function to swap the contents of EX and ESP. So if this is possible, like shouldn't there be something in C where we can swap the contents in one line instead of having a temp variable? Shouldn't higher level languages take use of this? The x86 architecture is explicitly aware of the stack. It has two dedicated instructions for saving and retrieving operands off the stack. push instruction pushes data on the stack. In specific, the push instruction can push the contents of a register, memory location, or immediate on the stack. It has one source operand. Its operation is shown in table 5.6. Conceptually, it first saves the value of the first operand as a temporary value temp. Then it decrements the stack pointer and transfers the temporary value to the top of the stack. In a 32-bit system, we decrement the stack pointer by 4. Isn't it very inefficient to keep shifting the values in the stack? But wouldn't it be better to have pointers to the stack that go up and down? When you're pushing a register, the processor knows its size based on the name of the register. For example, if the name of the register is AX, its size is 16 bits. If the name of the register is EX, its size is 32 bits. However, if you're pushing a memory operand or constant, the assembler cannot determine the size of the operand. We might be intending to push 2 bytes, 4 bytes, or 8 bytes onto the stack. In this case, it is necessary to indicate the size of the operand to the assembler such that it can generate appropriate binary code. In ASM assembler, we specify this information as follows: push dword ESP. Modify dword double word represents the fact that we need to push 4 bytes on the stack. So we have byte, 8 bits, word, dword, so double word, and then quadruple words. For pushing in the value of the immediate values, NASM assumes they are by default 32 bits long. We can override the setting by specifying a size modifier in the instruction. On the same lines, we can define a pop instruction as shown in figure in table 5.6. Conceptually, the pop instruction saves the top of the stack in a temporary location, then proceeds to increment the stack pointer by 4. Then it saves the temporary value in the destination. The destination can either be a register or a memory location. The push and pop instructions thus make workings with the stack very easy in x86 assembly programs. What is the final value of EBX? So move 10 to EAX, push EAX onto the stack. Move what's stored in the stack to EBX. So this over here outputs what is on top of the stack, right? Let me read again. Where did it go? Okay, yeah, that's what it does. So push ECX. ECX goes into a temporary variable. ESP decrements by 4. Oh yeah, we are pushing. So it assumes it's 4 unless we specify these modifiers, right? And then temp is ESP. Okay. So this square bracket ESP refers to whatever is stored at the top of the thing. What is the final value of EBX? So ESP, move it to EBP, 10 goes to EAX. And then EAX goes to the top of the stack. You're not pushing, you're just moving to the top of the stack, right? You're rewriting the contents of the top of the stack. You're not pushing or popping, right? So EPS, double word, we are pushing down a double word. And then EBP, the memory location of EBP minus 4 goes into EBX. EBP minus 4, or EBP before it contained the top of the stack. Now we pushed a double word. And we are going 4 bits, not bits. It's 4 bits, right? 4 bits behind. Okay. Note that ABP and ESP are essentially the same. After we push a value to the stack, ESP gets decremented by 4. Hence, the new indication of the top of the stack is equal to ABP minus 4. Since we push the value of EAX to the top of the stack using the push instruction, the value of ABP is equal to 10. New indication is this. Since we push the value of EAX to the top of the stack using the push instruction, and let me see what push does. Was here decrement. You're pushing a double word onto the stack. What is when we push? What exactly are we pushing? Why are we pushing the memory location of ESP? So what we are pushing on top of the stack is the address of the stack. Okay, so from this example, from push EAX, we have something stored in EAX. Wait, hold on. Hold on a minute. My tablet is not working for some reason. Um, oh, now it's working. Okay. So when I hear push EAX, I'll just turn it into. So when I see push EAX, push E, it's ECX. So what I'm hearing, what I'm thinking is that push EAX, we have a stack, all right? Stack decrements by 4. Wouldn't it be better? Okay, never mind. You have a stack. ESP points here. But if we decrement it by 4, let's say, yeah, this is the array. We decrement it by 4, it then goes up here. And then this goes to the top, goes here, and then temp is stored whatever memory address of this, and then the value of EAX is stored over here. ECX, I mean, the value of ECX is stored over here. But I do not understand what this thing means. Push double word APS. push double word ESP. From what I understand is that instead of, so the ESP decrements and then instead of the value you store is the memory location of ESP itself. That's what I'm understanding. It's the value of ESP itself. The value of ESP. No, wait. Let's say the value of ESP, we store 10 to EX. So this is what happens. ESP is over here. We store 10, right? We move 10 to whatever ESP is pointing to. And then what push double word does, the shorter form of these three statements, the memory address of ESP is stored in a temporary variable, ESP decrements. Is square brackets the memory? Is square brackets the memory address of or the value stored in that memory address? I think it's the value stored in that memory address, right? So temp value stores 10, and now temp goes. Why does it fill? Weird. Maybe I have to do this. Anyways, so 10 goes here, right? I don't know what is this? Draw solid dash draw. Fill solid, fill none. Okay. And then when we finally do EBP minus 4 to EBX, EBP was the original, EBP was the location of this. And then EBP minus 4, it's now this, right? So 10 goes to EBX. 17 EX pushed onto the stack, pop double word value of E. When they do something like this, it confuses me. Okay, the answer is 17. Let us discuss the rich set of area instructions that x86 processors support. Table 5.8 shows the add and subtract operations that are typically used in x86 processors. The basic add and subtract instructions are the values of the first and second operands. Read the first operand, also as the destination operand. They set the carry and overflow fields of the E flag register. The ADC instruction adds its two source operands and also adds the value of the carry bit. Similarly, the SBB instruction subtracts the second operand from the first and then subtracts the carry bit from the result. They can use the ADC and SBB instructions to add and subtract very large integers. So ADC adds its two source operand, also adds the value of the carry bit. The SBB instruction subtracts the second operand from the first and then subtracts carry bit from the result. So normal add, normal subtract, add carry, subtract carry. Well, why B? Why not SBC? We must operate on the lower bit. While operating on the higher bits, we need to take the carry generated by the adding or subtracting the lower bits into account. Use ADC and SBB instructions respectively for this purpose. Increment, decrement, and negative. Table 5.9 shows the semantics of increment, decrement, and negate instructions. The increment adds 1. Okay, the decrement subtracts 1. The negate instruction computes the negative of the value stored in the first operand. Okay. These three has nothing to do with carry bit, right? Increment, negate, write in x86 assembly code snippet to compute ax equal to -1 times ex plus 1. Eax increment and then negate eax. Okay. Compare instructions, compare. All right. So compare would subtract the two and check the zero flag, right? Compares two operands and sets the values of of a few flags. Performs a comparison by subtracting the value of the second operand from the first. This is conceptually a subtract instruction that does not have a destination operand. Yeah, but it sets the zero flag, right? Uh, Sign multiplication and division instructions in x86. They are known as I multiply and I divide respectively. The unsigned variants of the instructions are known as mul and divide. They have exactly the same semantics as their signed counterparts. The signed instructions are more generic, hence we only discuss their operation in this section. The IML instruction has three variants. The one address format variant has one source operand, which can either be a register or a memory address. The source operand is multiplied with the contents of EAX. IML, integer multiplication, we have integer division. I understand multiply, but how does it divide? We require at most 64 bits to save the result. Hence, to avoid overflows, the processor saves the result in the register pair. EDX contains the upper 32 bits and EX contains the lower 32 bits of the final product. The two address format version is similar to the other AIDU instructions that we have studied. It multiplies the first and second source operands and saves the result in the destination register. Note that in this variant of the multiply instruction, the destination is always a register and the result is truncated to fit in the register. The IML instruction has another variant that requires the operands. Here, it multiplies the contents of the second and third operands and stores the product in the register specified by the first operand. For this variant of the IML instruction, the first operand needs to be a register. The second operand can be a register or memory location. The third operand needs to be an intermediate value. So for three addresses, this one is an offset, right? Or no? Write an assembly code snippet to multiply 3 with -17. Oh, no. I got this wrong. Uh, so, wait. Destination, source, and the other source, right? The I division instruction takes just one operand. It divides the contents of the register pair EDX, EAX. EX contains the quotient and EDX contains the remainder. So it's always EDX. But why does it say EBX over here? Divide EDX EX by the contents of the EBX. Hold on. Divide the contents of the register pair EDX EX by the contents of the operator. Saves the quotient in EAX and the remainder in EDX. Note that the remainder has the same sign as the dividend. A subtle point should be noted here. While using a positive dividend that fits in 32 bits, we need to explicitly set EDX to 0. And for a negative dividend that fits in a 32 bit, we need to explicitly set EDX to -1. Okay, so the division part is confusing. So it's always EDX, right? Write an assembly code snippet to compute k to the power of 3, where k is the contents of ECX. So move ECX to EAX. I multiply ECX. I multiply. So if we have one register, then we assume, then we multiply it with EAX, right? EDX contains upper 32, EAX contains the lower 32 bits. Upper 32 and lower 32. Write an assembly code snippet to divide minus 50 by 3. Save the quotient in EAX and the remainder in EDX. So move -1 to EDX. Move minus 50 to EAX. So move 3 to EBX. Okay, so what we have here is, hold on, divide EBX. At the end, EAX contains minus 16 and EDX contains -2. There's one thing I don't understand. Yeah, so EAX and EDX, what do they contain? Save the quotient in EAX and the remainder in EDX. Divides the contents of the register pair EX, EAX by the contents of the operand. Oh, I think I get it. If -1 is saved to EDX, the entire contents of EDX would be 1, 1, 1, 1, 1, 1, 1, 1, like that. And then if you do -15, EAX would start with a 1, right? So together it will be a large number of ones, all the way till the first bit of EX. And then the number stored in EDX EX pair. So it's EBX divided by the pair, right? So it's 50 divided by 3. That's what we are doing, right? -50, I mean. Now we have logical instructions and or XOR not. Shift instruction, Shift AR, Shift HR, Shift AL, SHL. Shift right by 3 units. Shift right by 3 units. Then shift left by 2 units. What is A and H? Semantics of shift instructions. SAR, shift arithmetic right, performs an arithmetic right shift by replicating the sign bit. SHR, shift logical right, shifts the first operand to the right. Instead of replicating the sign bit, it fills the most significant bit with zeros. Wait, what do they mean by arithmetic? Do they mean like with that when we shift right, the first bit goes to the last? Okay, wait. No. Yeah, 1 0 1 1 0 1 0 1 2 3 4 1 2 3 4. If we do arithmetic, shift arithmetic right, all this would remain the same, right? And no, this is left. No. It goes right. 1 0. So it goes in the right direction. And the 0 goes at the end, right? And if we do SAR again, 0 1 1 0 1 1 0 1, we bring this to the right. What if we do left 1 0 1 1 0 1 1 0 like that? I might be wrong, but and if it's a normal shift right, SHR, it doesn't shift the first bit disappears, the most significant bit is just 0. What is the final value of EAX for dead C0DE? Shift by 4. You have dead C0D. Where is the E? Oh no, we did logical shift. As for arithmetic shift, dead C0DE. Now we have F dead C0D. Why F? Why not E? Let me think about this. 4 bits to the right. Why F? Shift left. D disappears and 0 at the end. Okay, left. Okay. This I understand. No, I don't understand. Why 0? You're doing an arithmetic one, right? Maybe I'm wrong about this. Doesn't do the clock thingy. And what did I mean by replicating the sign bit? Wait, I need more samples of this. Hold on, this is going to bother me. Wait, let me just search it online. x86 SAR versus SHR. Logical shift, logical right shift. When bits are shifted to the right, the vacated bits on the left are filled with 0. Okay. Arithmetic shift right, shifted to the right, the vacated bit positions on the left are filled with a copy of the original MSB sign bit. This preserves the sign of the number, meaning a positive number remains positive, a negative number remains negative. So 1 0 0 1 0 0, shift to the right, come 1 1. Oh, so for the most significant bit, the most significant bit isn't going to change with arithmetic right. So 1 will remain 1, 0 will remain 0. This preserves the sign. Okay, now I understand. So I was wrong about this. It's not a clockwise, but there should be a thing like this, right? Or maybe it's only in the ARM processor. Conditional and unconditional branch instructions. Jump to full. And then what is this? Jump to full, but condition code. Or do we set the flag in here? The flag bit? Overflow, no overflow, below, not below, equal. Below equal. Sign bit is 1. Sign bit is 0. Less than or equal. Greater than or equal. Table 5.14 shows the semantics of branch instructions. Jump is an unconditional branch instruction that branches to a label. The assembler internally replaces the label by the PC of the label. x86 defines a series of branch instructions with the J prefix. These are conditional branch instructions. The J prefix is followed by the branch condition. The conditions are shown in table 5.15. For example, the instruction JE means jump if equal. If the last comparison has resulted in inequality, the processor branches to the label. Otherwise, it executes the next instruction. The condition is not satisfied. The conditional branch is equivalent to a NOP instruction. We would like to advise the reader at this point that the best method to learn assembly language is actually by writing assembly programs. No amount of theoretical reading can substitute for actual practice. Yes. But I want to see the output of my result. Okay, let's see. Write a program in x86 assembly to add the numbers from 1 to 10. So move to 0, EBX is 1. How about this? I have output over here, right? And then forget X and Y. Um, move message, EDX length, move sum. So where is the part where it displays this message? And for some move int um okay, if I don't touch this, hold on, let's say sum is 0 and I don't touch, I get rid of this, what happens? Error, operation size is not specified, LD cannot find dot o, operation size is not specified. Okay, let me see. No, I want this to remain output. And then if I execute, they say output 8. Where is this sum coming from? The location of sum. Sum is mentioned here. But if I get rid of this and do sum as 10, then what happens? Why do I get this error? What's so special about this code over here? DB. Okay, let's say I do this. Okay, I think it's the EAX that's confusing. So I will write this as 10. Now I'll get rid of these two. Now let's see. This is an immediate value, right? Or is there something missing here? Move 0, move 4. Yeah, but okay. Why is this not working? I want it to display. Oh, yeah, the character. Yes, yes, yes. 10. Okay, now I understand. So 0 is a character. Cannot display the number, it has to be a character. Right. EAX will store 10. And now we have move. Wait. Why is it doing that? EAX. Subtract. Okay, let's forget X and Y. Let's do our coding over here. So add numbers from 1 to 10. So let's say EAX. X is the number 1. Right? Okay, this one. X is the number 1 and we need to add 10 to it. So I'm going to do a loop dot loop. Then I'm going to add 10. So add. So move to EBX. No, I just need to increment it, right? Why am I doing this? My laptop is really slow. So increment EAX, right? And then branch if equal. No, jump if equal. Jump. So compare EAX with the number 10 and jump if not equal to loop. So and then write a program to add numbers from 1 to 10. Increment no, not increment. Add numbers from 1 to 10. This is the index. EAX is the index. EAX is 0. The starting is 0, right? And then EBX will contain the number. So move EBX 1. That's the index. And then increment EBX. We compare EBX with 10. First we add EAX, EAX, EBX. We add the index to EAX, compare the index with 10, and then we loop. Let's see. increment EBX, we keep adding, jump not equal. Invalid combination of opcode. So that's line number 22. What is invalid about add? Let me see. Add. Where is the add function? Where is the add function? Add and subtract. Add. Oh, there are only two. So output is, what is this, 1? How is the output 1? Compare EBX to 10 and then increment EBX. Let's see. So add 1 and then we add 2 and then we add 3 and then we add 4. But why is it not outputting properly? Oh yeah, this doesn't work for multiple digits, right? How do I view the contents of the thing? The problem with this is I can only display single digits. I want to display, I want to see what the value of each register is. Or what did I click? Never mind, I will just read the code then. I would have done the exercise. Like, I really want to practice it. But okay, so we are adding, incrementing the index, pairing it. That's what I jump less than or equal to. If it's less than or equal to, we jump. So not equal to. Write a program in x86 assembly to test if a number stored in EAX is prime. Save the result in EAX. If the number is prime, set EAX to 1, otherwise set it to 0. Assume that the number is greater than 10. Starting indexes to ECX contains the original number. Required for correct division. Wait, what? Oh, yeah. This upper 32 bits is set to 0. Compare, not prime. If the number is prime, set EAX to 1. So if it's successfully, if the remainder is 1, then we jump to not prime. Otherwise, we assume it is a prime. Okay. Unlike ARM and simple RISC, x86 does not have a return address register. The call instruction pushes the return address on the stack, jumps to the beginning of the function, as explained in table 5.16. Similarly, the return instruction jumps to the top to the entry at the top of the stack. Entry at the top of the stack needs to contain the return address. Return instruction subsequently pops the stack and removes the return address. Let us now consider a set of examples. Write a recursive function to compute the factorial of a number stored in EAX, save the result in EBX. So move EBX compare to 1. Default return value. Jump if equal dot return. So okay, so the number is stored in EAX, right? Number is 1, we just return. Otherwise, we push EAX, save the input on the stack, decrement EAX, call factorial. It's a recursive call. What's the difference between call and jump? Push the return address on the stack, jump to label.foo. Oh, I see. We call factorial. When we do a return, we start from this point, right? And then we do a return again. We go out of the function call. Okay, I understand. Pop EAX, retrieve input, multiply EBX. Okay, I think I understand. Use the stacks to store only those values that are overwritten by the callee function. It is now use the stack to pass arguments to the factorial function. Write a recursive function to compute the factorial of a number stored in EAX. Save the result in EBX. Use the stack to pass arguments. Wait, what? Factorial. Pass arguments to the factorial function. Move 1, compare EX. Get the value of EX from the stack. Okay, jump if equal. If it was only 1, then just return. Push EAX on the stack. Decrement EAX, push. Wait, what? Push EAX on the stack. Decrement EX. Save the argument. You're pushing twice. We push once, decrement it, push it again, and then call factorial. Pop EX again. Pop 2 EX, and then retrieve the value of EX again. Why we pushing? Oh, there are 2 arguments, right? So that's why we pushing twice. But when do we use those 2 arguments? Pop EX, retrieve the value of EX. Why are we pushing twice though? Then the stack pointer gets automatically decremented by 4 after a function call. The argument EX is available at ESP plus 4 because we push it on the stack just before we call the function. To call the factorial function again, we can push on the stack and then pop it out after the function returns. Move ESP plus 4. Yeah. Push, decrement, push. Okay. So one value of EAX is push on the stack and then decrement. And then the decremented value is pushed on top of that stack. And when we call the function, we pop out the 2 stack values. Wait, we pop it and we store it to EX. Call factorial. Oh, no. When we call factorial, we go back here. Move 1 and then compare. Return. And when we do return, pop. Okay, I think I understand. Let us now assume that we have a lot of arguments. In this case, we need to push and pop a lot of arguments from the stack. It is possible that we might lose track of the order of the push and pop operations, and bugs might be introduced in our program. Hence, if we have a lot of arguments, it is a better idea to create space in the stack by subtracting the estimated size of the activation block from the stack pointer, moving data between the registers and the stack using register move instructions. Let us modify our factorial example to use move instruction instead of push and pop. Move one. Okay. So subtract, create space on the stack. Move EAX, decrement, and then move EAX. Push the argument, call factorial. Retrieve EX, multiply, and then store the stack pointer. Okay, this part still confuses me that we are popping two values. When the value of EX got replaced. Or maybe we don't need the first one, I guess. However, this method is also not suitable for large functions and complex programming languages such as C++. In a lot of C++ functions, we dynamically allocate space on the stack. Most of the time, in such cases, most of the time, you do not know the size of the activation block of the function in advance. Hence, reallocating an activation block becomes difficult. We need to dynamically keep track of the size of the activation block of the function. This introduces additional complexity, additional code. It is a better idea to save the value of ESP in a dedicated register at the beginning of a function. At the end of the function, we can transfer the saved value in the register to ESP. This strategy effectively destroys the activation block. Most of the time, we use ABP register to save the value of ESP at the beginning of a function. This register is also referred to as the frame pointer. Now, it is possible that the function might follow the same strategy and override the value of ABP set by the caller. Thus, in this case, ABP needs to be a callee saved register. And if an invoked function overrides the value of ABP, it needs to ensure that by the time it returns to the caller, the value of ABP is restored. By using the base pointer, we do not need to explicitly remember the size of the activation block. We dynamically allocate data structures on the stack. Let us augment our running example with this feature. Write a recursive function to compute the factorial of a number stored in EX. Save the result in EBX. Use the stack to pass arguments. Avoid push and pop instructions. Second, use the EBP register to store the value of the stack pointer. Factorial. We are moving the value from the stack to EAX. Push EBP. Wait, what we supposed to avoid push and pop? Use the EBP registers to store the value of the stack pointer. Move ESP to EBP. Move one to EBX and compare them. If it's just one, then return. Now here's the recursive step. Subtract 8, create space on the stack. Move ESP plus 4 EX, save the input on the stack, decrement, then push the argument. Do the recursive call. Of course, if it's 1, then just return. And when we do return, we move, retrieve the input, and multiply EBX with EAX. Doesn't EBX get overwritten over here? We set the old value of EBP on the stack and set its new value to the stack pointer. And lines 4 and 5 respectively. At the end of the function, we restore the values of ESP and EBP in lines 21 and 22. Stack management instruction. Enter and leave. Enter immediate 0. Enter 32 0. So push EBP, push the value of EBP on the stack. Move EBP. And then ESP, save the stack pointer in EBP. Okay, so move ESP to EBP. and then ESP minus 32. And leave EBP, pop EBP, semantics. The four extra lines added in example 77 are very generic and typically part of the most large functions. Programmers can add them in if they're writing assembly code, or compilers can add them during automatic code generation. In either case, using the base pointer is a very convenient mechanism to manage the stack and to destroy the activation block. Since these set of instructions are so commonly used, the designers of the x86 ISA decided to dedicate two specialized instructions for this purpose. The enter instruction pushes the value of EBP on the stack and sets its new value to be equal to the stack pointer. Additionally, it is also possible to set the initial size of the activation block. First argument takes the size of the activation block. If we specify 32 as the first argument, then the enter instruction decrements ESP by 32. So what is 32 exactly? 32 is our argument, like thing we want to push. We decrement the stack pointer by 32. But like, what's the context of this? Note that during the course of execution of the function, the size of the activation block might continue to vary. Second argument for the enter instruction correspond to the nesting level of the function. We shall refrain from discussing it here. Interested reader can refer to the references mentioned at the end of the chapter. We shall simply use the value of 0 for the second argument. It's possible to set the initial size of the... Okay, so first, okay, it's just the size of the activation block, right? The leave instruction performs the reverse set of computation. It first restores the value of ESP, then the value of EBP. Note that the leave instruction is meant to be invoked just before the return instruction. We can thus augment example 77 to use the enter and leave instructions. Secondly, we can omit the statement that subtracted 8 from ESP, because this functionality is now built into the enter instruction. So factorial move EAX, get the value of EAX from the stack, enter 8 0, so activation block 8 blocks, save EBP and ESP, decrement ESP by 8. Let me think. Decrement ESP by 8. Okay. Move EBX. So move 1 to EBX, default return value, and compare 1 to EAX. Compare number with 1. Oh, so if the number is 1, just return. If it's not 1, we continue. Save input on the stack. Decrement the number. Then push the argument. Go back to factorial. It's this part that confuses me. Don't we reset the value of EBX? When we return, leave load SPBP return, EBX is still 1, right? We multiply EBX by EX. No, wait, I think when we are doing the multiplication process, EBX will never turn into 1, maybe? Yeah, I think that's the case. Lastly, we should mention that x86 processors have an op instruction that does not do anything at all. It's mainly used for the purpose of ensuring correctness in modern processors, for ensuring blocks of code are aligned to 16-byte or 64-byte boundaries. It requires the latter functionality for better behavior at the level of memory system. Okay, I'm going to end the stream here, and then I'll have to do something. I will continue the stream after I'm done with something else, and then I'll read the rest of the chapter. Anyways, I will end the stream here and see you guys next time. Bye.